Okay, let's start. So the first question is, interatomic separation is a function of potential energy, pressure, temperature, or charge state. There can be multiple answers correct. So let's say a simplified system of only two atoms or any two particles, then on what factors does the separation depend?
Good afternoon, sir.
Good afternoon. So, for answering this, we can draw the Lennard-Jones potential for two particles. If we draw the Lennard-Jones potential, so I'll just write here. So y-axis, x-axis, y-axis is the potential energy, x-axis is the distance between atoms. This is the distance. So this distance is t, let it be d. If we draw the potential between these two atoms, it will look something like this. With this at infinite distance, the potential difference between them will be equal to 0. So if you look at this at the value that is created here, it's not completely parabolic, it's not completely a harmonic potential. So what we have here is, like, this would have been a completely harmonic potential, but it's not like that. There's anharmonicity associated with this. So if you want to draw the mean distance, so if you, let's say, apply temperature, if you apply temperature, uh, then you are actually applying energy in the form of, which is equal to kBT. That is the energy that you are applying. If you are applying pressure, then you can think of it as a spring mass system, in which you can either apply like a tensile stress or a compressive stress, and then you can increase or decrease the pressure. So if you apply a tensile stress, if this is the mean position, if this is the initial mean position, if you apply tensile stress, it will move somewhere here, it will move here, and so the interatomic separation will increase on applying on applying a tensile stress on the on the two particles in the spring mass system. So it's like a tensile force, and if we decrease, if we apply a compressive force. So interatomic separation is a function of pressure. If you apply temperature, then you apply an energy in the form of kBT, and this increases the energy of the system. This is the energy. And so effectively increase the energy of the system. And if you look at the mean position, I will draw this value again. If I redraw it, it looks something like this. So the mean position moves around. The distance keeps on increasing with an increase in temperature, or when you apply energy to the system. This is the distance d. So on applying temperature, the spring expands because of application of extra energy to the system. It can also contract because both of them are like high energy systems, but uh, the mean in general will increase. So it when you apply temperature, it will vibrate. Like both of these atoms will vibrate, but it will tend to vibrate. If you look at these particles now, so I will redraw it. So if you look at these particles now, these two particles were initially like this, connected with the spring, and applying temperature, the mean position it shifts this much on compression, but this much at on expansion on increasing the temperature. Say when here this much compression and this much expansion, so the mean position in effective increases on increasing the temperature. So the temperature also increases increasing temperature increases the interatomic uh, separation. Lastly, for potential energy, we see that irrespective of, like, this is the potential energy, right? Like here and here, in both these places, the potential energy is higher. And so if you are at either this state or this state, what it means is that you're storing energy in the spring. So if it's a simple classical system, could have done half kx square, like with half k delta x square, where delta x is the elongation in the spring. So you can either compress or you can expand. In both these cases, you can apply some kind of potential energy. And so even the application of potential energy, either compressive or tensile, can increase the interatomic separation or decrease the interatomic separation. Is this clear?
Yes, sir. Okay, sir.
Okay. We had discussed it in, I think, in the first or the second class. It's again revisiting the previous lecture. So, which of this modeling system is relevant to metallic systems? The free electron model, nearly free electron approximation, loose binding approximation, Stirling's binding approximation.
It's B, sir. Nearly free electron approximation.
Yes, right. So basically, both of these are correct answers, because we initially, what it means is the Drude model. This is the Drude model, where we say that, okay, all the molecules are all the atoms are all the electrons are basically a kinetic theory gases can be applied to them. So all electrons are free, and then we say that, okay, like only the electrons that are confined within the geometry are applicable, and so which are the nearly free electrons. The truly free electrons are actually can also move outside the boundary of the system. So both of them are correct, both A and B. uh, okay, I mean, both of them are correspond to the same uh, model.
Sir, actually,
Mm-hmm.
when there is a free electron means it will not come under the system, right, sir? Sir have said is it, when in a material there is a free electron means it will be out of the system, right?
Yes,
It will
right. So
be
that's what.
nearly free electron only.
Yes,
So
yes.
it will not be when there is a free electron system. When we are speaking about a free electron system means it will not come under metallic, right, sir? It will be out of the metal.
Yes, right. So it is when we say electron system, it's the Drude model was a free electron model, and then we say, okay, I'll draw it all. I understand your question.
Yes,
What
sir.
you say is that, okay, if I draw it again here.
It's actually I can understand, but it is actually failure, right? Failure
Right.
model.
It's a failure model, but the second, okay, you can say that the option B builds upon option A.
Okay.
Option B is built upon option A. So, I mean,
Yeah, it's actually built
uh,
upon option A.
right, right.
And the question is relevant to metallic system, right, sir?
Yes, right.
So I think B only the answer, but A when we are speaking about free electron, it is out of the material.
Yes.
when but
Uh-huh.
is a free, it will be out of the metric, right, sir?
Right. So the impact of the crystal is not involved in the free electron system. We just say that okay, electrons is a gas. We do not
Yes.
consider the existence of ions or atomic atoms in the or the crystal in the system. That is
Okay.
considered only when we have the nearly free electron approximation. You are right. So even I agree. So first you do the free electron system, and then you perform the nearly free electron approximation on top of this, on apply to the Drude model, and then you like that is relevant to the metallic system. Actually, it's not a complete model. Like there are further approximations that are done, many more approximations that have been involved.
Okay. Okay, sir.
So they like even like the chronic penny model and everything. Although that's not much relevant to metals, but even those are relevant to the crystalline systems. So I understand your problem. You are saying that okay, like if we draw a potential versus like distance kind of a plot, then we have something like this.
Yes, sir.
And so this is the geometry. This is the length of the system or the dimension of the system of the material.
Yes, sir.
And then you have ionic cores here. So only electrons in here can participate in the
Conduction process. Sorry.
processes, which are the nearly free electrons. And if it is like fully free, then it can be anywhere in the, like it can be here also, outside the bounds of the geometry of the system.
Yes, sir.
You're right.
What I have said means because when it is a free, it will not be convention the material. Right? That is why I am asking.
Yes, right. You're correct.
Okay, sir.
But like it is built up also, the concepts of all
Okay.
the like the conductivity and everything is, it comes from the Philetron model,
Okay, sir.
where we
Okay.
have the Drude model, and then you have the Drude Sommerfeld model, and then you and like apply all the quantum mechanics principles. You apply the Bloch theorem, and they apply the chronic penny model, and so like option A is not incorrect. That's what I want to say.
Okay, sir.
And also, okay, so there is nothing called loose binding model. There's something called the tight binding model, which is more. Uh, it's called the tight binding model. It's not the loose, and it has been found to be more useful for insulators. Okay. So this is the third question. It's a match the following question. So okay. So you have to match them. So intrinsic semiconductor. So okay, let's first take the this element C and D. Indium, it's a it is a 3,5 semiconductor, 3A5A. So indium is here and antimony is here. So indium antimonide is the 3,5 compound. So one of the options is 3. P-type silicon is a extrinsic semiconductor. So silicon is here. To make it p-type, you can dope it with gallium, boron, aluminium. So okay, gallium doped semiconductor is also a p-type silicon, can be a gallium doped semiconductor. Okay, now the uh, temperature dependence. That this is something that is very interesting. So temperature dependence is seen only in the case of extrinsic semiconductors. So if I draw the uh, carrier density concentration versus temperature, charge carrier concentration, and in the excessives we have temperature. So first I'll draw for intrinsic semiconductors. It will look something like this. So it will be close to the, it will be close to 0. Then it will shoot up. It should be more. So it will shoot up like this. So to explain what is happening here, so again, when you apply temperature, it's basically application of energy in the form of kbt, which is energy. So if you have an intrinsic semiconductor, this is the conduction band, this is the valence band, and this is the energy between them. This is the E band gap. Let's call it Eg. So if I draw it in the form of like this representative, at lower temperatures, the value of kbt is only equivalent to this much, whereas at very high kbt it can be equal to this much. So what happens? Just the temperature is enough to move an electron from the valence band to conduction band when the kbt values are very high. At high temperatures, this is at low temperatures. So at high temperature. This is equal to the value of kT. So at high temperatures, the value of kT is enough to move an electron from a valence band to conduction band, and then you can have electrons in the conduction band, which are basically charge carriers. So this should be with respect to this. This is the critical value of temperature kBT, which sort of corresponds if you extend it up like this. So this value, let it be E1. So in this case, this is equal to E1 equal to Eg equals to kBT. So this is at temperature. Sorry, this is at temperature T1. So at T1, the value of the thermal energy is equivalent to the band gap approximately, and there is a steep rise in the carrier concentration. And as you further increase the value of temperature, you provide more amount of energy. This is like an even high temperature, and so there's an even larger concentration of charge carriers, because it becomes much more and more easier for the electrons to go to the conduction band. This is understood, right? What I wanted to say in this.
Yes, sir.
So now if you take the example of extrinsic semiconductor, what is seen is that it initially increases, then it becomes stable, and then it again starts increasing. So there are 3 zones for extrinsic semiconductors. So let it be zone 1, zone 2, zone 3. So the concentration is constant here. So let's again try to draw it and understand what is happening. So this is at low, let's call it low temperature, medium temperature. It's actually range, but okay. Let us call it high temperature. So at low temperature, Let us consider both n-type and p-type semiconductors. This is the, just magnify it. This is the n-type. This is the p-type. Conduction band, valence band. This is the Fermi. Conduction band, valence band. This is the Fermi. So at low temperature, again the value of kT is very low. So maybe the value of kT is only this much, and in this case it's only this much. So electron transitions from the EF to conduction band is not possible, and from the valence band to conduction band is obviously not possible because that requires a much higher energy, which is why the carrier concentration is very low. The probability of electrons to reach from the valence band to the Fermi level is very low in the case of p-type, and from the Fermi level to the conduction band is very low in the case of n-type. What happens at moderate temperatures? So this is why at low temperatures the carrier concentration is very low. At moderate temperatures, if I again draw this, conduction band, valence band, conduction band, valence band, the Fermi level. So in this the energy is sufficient to remove an electron from the Fermi level to the conduction band, and in this case from the valence band to the Fermi level. So so basically the dopants, like for example in the case if it's a boron doped silicon or natrium doped silicon, then in the case of boron doped silicon a hole is able to form, and in the case of nitrogen doped silicon we are having an extra electron. But if you again draw it from here, if you draw the same dimensions from here, so this is allowed, this is allowed, and this is allowed. But if I draw it again from here, it's only this much. So electron from valence band to conduction band, this motion is not allowed. So this thing is not allowed, which is why we see that this is a constant concentration here, which is corresponding to only the dopants. This is like because of dopants in the system. Now in the high temperature regime, so if we again draw this, so in this case you have sufficient energy that is applied. It would be this much. So this is equal to the value of kT. So in this, electrons can make transitions like this from the Fermi level to the conduction band, as well as to the valence band to the conduction band. Both of these are allowed. Both of these are allowed. Now we know that the concentration of dopants is much lower. It's like it's much lower than the concentration of the base element. If let's say you have a boron doped silicon, the concentration of boron is much lower than the concentration of silicon. So this process will dominate. This process will dominate over the effect of dopants, just because of the concentration difference. And so it will. So this value is saturated. This value is already saturated in moderate, and you have an extra effect that is seen because of the intrinsic effect of movement of electrons from the valence band to from the conduction band because of silicon, if it's a doped silicon. and so it again behaves like an intrinsic semiconductor. So it behaves like an intrinsic behavior. So for all practical temperatures, so we can ignore the high temperature regimes because at that places semiconductors are not usable. So we see that the extrinsic semiconductor is much highly dependent, is strongly dependent on the temperature, the amount of carrier concentration and all. So we can say that the extrinsic semiconductor behavior depends on the temperature. So one is also an option here. Is it? Did you understand what I tried to say in this in my argument? Okay.
Yes, sir. Yes.
Okay. And the extrinsic semiconductor obviously depends on the dopant's concentration also. That's why it's extrinsic. P-type silicon will also depend on the dopant concentration. 3,5 compounds will be intrinsic semiconductors. So A3. Okay, sorry. Uh,
Sir, actually, the
ha ha ha
intrinsic
ha. Right, right,
depends on temperature, right?
right. Ha, ha.
But extrinsic is based
Yes,
on
yes, right.
dopant
Yes, yes,
one
yes.
and
Yes,
A1
right.
B.
It's one here. Yes, yes. I made a wrong statement. The intrinsic depends on the temperature. That's why we have this. So it's mostly stable for extrinsic. It's independent. It's a constant. But whereas for intrinsic it depends on the temperature. You're right. You're right. So A1, B2, C3, D4 is the correct option.
Yes,
A3,
sir.
this will also be Galbert's equation will be extrinsic. So A4, A3, B4. This is intrinsic, so B1, and D2 is also correct answer. So both A and D are correct answers for this. Mm, I hope I'm correct. A1 and 3, B2 and 4, C3 and 1, D4 and 2. Okay, right?
Okay, sir.
Okay. So using the below energy wave vector diagram, we can get the information about the dash of light radiation required for electron transitions based on the difference between A and B values. So this is the band gap. So if let's say let us call it EG. So we can write, so obviously this AB is EG, so we first of all know the band gap. You can write EG as H nu. So you can, from this you can get H is the Planck's constant. So you can calculate the frequency. Then you can also write it as Hc by lambda, from which you can get the wavelength of light, speed of light, and H is the Planck's constant. So from this you can find out the wavelength, frequency, and band gap. You can find out the intensity from this. Okay, is it? This is an easy question. Understood? We'll move to the next question if there is no more question on this. A direct bandgap material needs dash for electronic transitions, while indirect bandgap material needs dash for electronic transitions. Acha. So one of them is a one-step process, another one is a two-step process. In the one-step process, we have only photon. In the two-step process, we have both a photon and a phonon. So the question is that in which of them we need what? So if we again have the EK diagram, okay, it's already here. So there is two steps here. This step one and step two. So initially, for step one, we need to have a photon. So this will apply energy, but negligible momentum. And in this case, we need a phonon. So we apply momentum, but negligible energy. So in the last class, we had solved a question in which we tried to find out the ratios of the energy and the momentum, and we found out that the momentum applied by a photon is 4 orders of magnitude lower than that of a phonon, and the energy applied by a phonon is approximately 10 to 100 times lower than that of a photon. So which is why we say that a photon only applies energy and a phonon only applies momentum. So, and that was an indirect transition in this case. So from this we can answer here. So a direct bandgap material needs photon, while indirect bandgap materials needs photon as well as phonon. Only photon, both phonon and photon. So option B is correct. Any questions? Hello, am I audible?
Sir, you are.
Okay. I hope there's no question. So uh, photons or phonons, which of these transmit energy and slash or vibrations from one atom to another? So the so when we talk about the lattice, in the case of photons, we do not consider the lattice. It's only phonons. Phonons are lattice vibrations. So phonons are responsible for transmitting vibrations as well as energy from one atom to another. Right? Okay. I hope there is no question with this. There's no doubt with this question. So we make a statement that atoms contribute to specific heat of the solids. So what else is correct along with this statement? In overall specific heat of solids, phonon contribution should also be considered. In overall specific heat of solids, photon contribution should also be considered. So this is the assertion. in one of our previous classes, we had found out the specific heat depends on the electrons, but even the because we had ignored the effect of lattice at that point of time, because even the lattice atoms are vibrating and transmitting energy, and so we know that lattice vibrations are called phonons, and as we saw the previous question also, that they can help in transmitting energy from one atom to another atom. So even in the overall specific heat of solids, phonon contribution is important. Photon is not important because it is not something that is originated inside the uh, crystal. You have to apply addition photons from outside, or you have to like apply some form of energy from outside the system to the system to create or absorb photons. So in this case, only assertion A is correct, not assertion B. And if you look at we had seen for the formula for the effect of specific depends of because of electrons. So this vibrational component is because of the phonons. So the specific heat is dependent on both the electronic and the vibrational component. And if you see that the electronic component is varies linearly with temperature, whereas the vibrational component, that is because of the phonons, it varies as a cube of temperature. And therefore if you again draw it, if you draw the specific as function of temperature, because of electronic contribution, it will increase linearly with time with temperature, but it will increase as a cube for phonons. And so we cannot it is absolutely important to consider the effect of phonons at high temperatures, and eventually it saturates at a value that is approximately equal to 3R, which comes from the Dulong-Pettit law, but we can ignore it for now. So this has a T cube dependence, and this has a linear dependence with temperature. This is because of electrons. This is because of phonons. So it's absolutely important to consider the effect of lattice vibrations when estimating the value of the specific heat. We can ignore the uh, pre-factor for the time being. The derivation for this you can find it in some book like Ashcroft and Burnbin or some Kittel or somewhere. You can find those definitions, the derivations there. So atoms contribute to specific heat of the solids, and in the overall specific heat of solids, phonon contribution should also be considered. Any question? Okay. So next question is about magnetism. So we have to match the magnetic susceptibility values depending on what type of material it is. If it's a ferromagnetic, diamagnetic, or a paramagnetic material. So this is a very short table of first of what is a diamagnetic, paramagnetic, or a ferromagnetic material. So in a diamagnetic material, this so atoms. So I'll write it on the right side. For diamagnetic materials, atoms have net zero magnetic moment. Which is why if you see here in this the spheres, no direction is given because there is no net magnetic moment. And when you apply a field, a magnetic field into this, what you see is that this material weakly opposes the field. So this is the definition of a diamagnetic material. In a paramagnetic material, atoms have a magnetic moment. So what happens? They individually have magnetic moments, but they are oriented in all directions. It is same as saying that the electrons, when you do not apply any potential difference, the electrons have a very high velocity, but the drift velocity is zero. Similarly, the atoms have a magnetic moment, but the overall magnetic moment of the sample is zero. The sample has no net magnetic moment. But when you apply an external magnetic field, it weakly reinforces the applied field. This is the definition of a paramagnetic material. And finally, for a ferromagnetic material, both atoms and the overall sample have a magnetic moment. So how does the overall sample have a magnetic moment without applying any field? It is because of orientation of all the individual atom in a particular direction, because of which there is a net magnetic field in one direction. So in this case, it strongly reinforces the applied field. So this is the difference between a diamagnetic, paramagnetic, and a ferromagnetic material. Now we spoke about if it opposes or reinforces the field, and if it's like a weak or a strong interaction. That depends on the magnetic susceptibility values. So if you write this, if you write an expression for this, maybe we can skip through the derivation for this. It's 347. Okay, we can skip to the derivation. If we write an expression for the induced magnetic field inside a solenoid. So if we have, let's say, if we have, let's say this is a solenoid. You apply a current here. There are n number of turns, length L, and then you put a material inside, and this material can be either a paramagnetic, diamagnetic, or a ferromagnetic material. And then you measure this. So because of this solenoid, there is a generated field which is generally denoted by H. It's generally denoted by H, and this H will induce a magnetic field inside the material, which is denoted by B. And there is an expression by B is equal to mu naught mu R H, or it is also written as mu naught into 1 plus chi into H, where chi is susceptibility. So basically mu r is equal to 1 plus chi. So when it reinforces, what happens is that the what does that mean? That means for the same generated field, the value of b increases, and so mu r is positive. Mu r is greater than 1. Therefore, chi should be greater than 0. So for reinforcement, for reinforcement, we can write it as b in the present. Okay, for reinforcement, mu r should be greater than 1, or chi should be greater than 0 for when there is a opposing field. So mu r uh, greater than 0, less, sorry, mu r will be less than 1, but it has to be greater than 0, and so chi will be less than 0. For weak, chi will be very close to 0, and if it is strong, then it will be much higher than 0. So now we see here. So we see that for ferromagnetic strongly reinforces. Therefore, it must be a positive value, and it should be highly positive. So we see that only this this value, a plus 10 power 6, is corresponding to ferromagnetic. So it's either option A, B, so these two can be answers. For paramagnetic, it again weakly reinforces the apply field, but it's weak. So it's still a positive value, but it's very close to 0. So both this can be answers. And for diamagnetic, it weakly opposes. So there should be a negative value and close to 0. So option A is for diamagnetic materials. So B, A, and A, B. So okay. So the answers are A and B. Diamagnetic materials have is option A, paramagnetic option C or D. Is it clear? Okay, we'll move to the next question. So the magnetic field, temperature, and current density are required to decide the superconductivity, a superconducting state of a material. So a material is superconducting because of uh, some particles, bosons, which are particles which are bosons called Cooper pairs. So superconductors have Cooper pairs. So what are these? These are pair of electrons, two electrons, which have opposite spin and opposite wave vectors. So now what happens? Basically, there are a pair of atoms. Now, when you apply a very high temperature, you can separate those two electrons away. When you separate those electrons away, what we have are single electrons, which are fermions. And so, the from bosons, there is transition to the fermions when you apply very high temperatures. So, if you are somehow able to break these Cooper pairs, the superconducting behavior is gone. So therefore, the high magnetic field. So this all these three quantities, all these three quantities, they can break the Cooper pairs. At high values. So you have to be at very low magnetic fields, temperature, and current densities to observe the superconducting state of a material. If you increase them, then the Cooper pairs will not be there anymore, and the superconducting nature will be gone. Therefore, all these three quantities are important for the superconducting state of a material: a low temperature, a low magnetic field, and a low current density. Okay, any question? No question. So the Hume-Rothery phase, forms at a specific ratio of which of these? Total electrons per atom, valence electrons per atom, total number of atoms per compound, certain atoms per compound. So these are also called electron compounds. So what is important is the valence electron per atom. This valence electrons per atom determines the Hume-Rothery phase. So the next question is about this, like what is the importance of this Hume-Rothery phase and the valence electrons per atom? So the question is that in electron compounds, which basically the Hume-Rothery phases, for a crystal structure to be BCC, base-centered cubic, body-centered cubic, face-centered cubic, or simple cubic, its EA ratio should be lesser than 1.4. So if we again revisit our last few classes, we started with the density of states. So if we have the density of states versus energy, and we saw that it has a behavior that which is like this. Then we studied the concept of Fermi-Dirac distribution. and corresponding to this value, let's say the Fermi-Dirac distribution probability distribution. This is the energy. We showed that if it's close to 1 here and it's close to 0.5 at the Fermi level, and so we have a distribution that is close to 1 and then it goes down like this. And so from this we can then draw the density of occupied states so density of occupied states which is like n of E. This is T of density of occupied states. So this is equal to the density of occupied states into the Fermi-Dirac probability. And so if we again draw it here, what do we see? It looks like this. It goes up, then it drops down. So this is how the density of occupied states will look like. Then we studied about the effect of the Brillouin zones, Bragg planes, the in the reciprocal space. So this is EF. EF. So we saw that there is diffraction at the Bragg planes. So then we again further improve this model. And we incorporate the effect of, so what do we do? So we incorporate crystal structure. And which also includes the Bragg planes, Brillouin zones. The concept of Brillouin zones, the concept of Bragg planes, diffraction. So we can we can include all this also. And what we see is that we saw that when we draw the EK diagram, so there is a diffraction that happens at the Brillouin zone boundaries, and we can plot that here. So we have energy here. Because of diffraction, it will look something like this. There will be a peak and it will go down. So we'll see features like this. Now, if we incorporate the effect of crystal structures, we see that, and further magnify it for the sake of discussion. It looks like, let me further, it can't come back, okay, be like this. So we see that it's known that in the case of copper or silver, for FCC, we get the in the distribution like this, the density of occupied states in this way, and for BCC it appears in this way. Now, if now this critical, the point of intersection is seen at E by A ratio of 1.4, which we are discussing. Why it is important? Now let's say you go beyond, let's say you go beyond 1.4, which is basically in this regime. So what we see here, we see that the density of states in the case of BCC is higher than in the case of FCC. So the final Fermi level, if it was in FCC, will probably lie somewhere here. If for FCC, but for the BCC, it will lie somewhere here. Let's say it's just 1.5 or something, 1.42 or something, slightly above. So just above 1.4, the BCC becomes more stable because the Fermi energy is of in the BCC case is lower than that of the FCC case. But let's say you slightly move towards the slightly lower than, let's say 1.38. In this case, FCC has a higher density of states than the BCC. So what will happen? What will happen is FCC will have somewhere here, let's say EFCC. In the case of BCC, because the density of states is lower, it will be somewhere here. So below 1.4, FCC is more stable, and above 1.4, BCC is more stable. The Fermi energy, as we had discussed, is similar to the chemical potential. The system will want to keep the minimum chemical potential. Just like random 1.42 just for discussion, and let it be 1.38 just for the sake of discussion. So just below 1.4, FCC is stable. Just above 1.4, BCC is stable. 1.4 is the point at which these two intersect. Therefore, in electron compounds, for crystal structure to be FCC is stable at below 1.4. Electron compounds, for the crystal structure to be FCC, its E by A ratio should be lesser than 1.4, and for it to be BCC, its E by A ratio should be greater than 1.4. So the answer is option C. Is there any question, any doubt? So that was the last question. If there are no more questions, since we are past 4 p.m., we can stop. This was the last class. If you have any more questions, you can post it in the NPTEL Q&A section. I will try to answer them there. So we can stop it here.